So how do we make code safe against buffer overflows? Well, one way is to, instead of using getS, you can use fgetS, which is a limited form of getS, which will read an input from the input and write it into this buffer, but no more than 64 bytes. It won't write more than 64 bytes into that buffer. In this case, 64 is an argument. So you can use fgetS and pass to fgetS and say, here's the amount of size available in the buffer. Don't write past the end. And then fgetS has some code in there that checks every time it's about to append another character. It checks to make sure it hasn't gone past the end yet, hasn't used up all the available space. So in general, that's kind of one approach, is you keep track of the length of all your buffers. You pass them along with every time you pass a pointer to a buffer, you pass along also something indicating how much space is available. And then the code that actually writes to it, before it writes to it, checks to make sure it's not going to write past the end. By the way, just as a little bit of stylistic stuff, I noticed there's that same number 64 in there twice, which is a little bit slightly mildly dangerous for a programmer, because if they decide, I need a little more space in the buffer, and they add that 64 at the top, but they forget to change the 64 at the bottom, then they might have a problem. So a slightly cleaner way to do that is in C you can use size of, which in this particular case, when you have an array with a fixed size that's declared like this, will indicate how much space, number of bytes available in it. But beware, doing these bounds checks can be a little tricky in C. So here's an example of vulnerable code that on the first sight looks like it might be okay. This code is doing a bounds check. Think of this function as one where the attacker is in control of the argument. Okay, so a string is being passed to us, and we're being told how long it is, or a memory, a sequence of bytes is being passed to us, and we're told how long it is. Assume the attacker, that came from the attacker. So the attacker chooses what the contents of that are and the length of that is. Now, it looks like we're okay here, because we allocate 64 bytes. We check to make sure that the length of the thing we're given is not more than 64 bytes. If it's 64, if it's too big, then we say, no, I'm not going to write it in here. But if it's small enough, then we say, okay, I'll write it into the buffer. So it might look safe on first glance, but I want to warn you of a gotcha here that makes this trickier than you might think. If we look at the declaration for memcopy is a standard library function that copies data from here to here. All right? You give it pointers, and you tell it the number of bytes you want it to copy. And it'll do the copy for you. Here's what I want to point out. The type of this argument is declared to be size underscore t. And if you don't know what size underscore t is, boy, you got my sympathies, because most people don't. But it's a slightly obscure part of C, which is basically a way of saying something like unsigned int. It's intended for representing lengths. And the length should never be negative. So it's declared to be an unsigned int. So now, here's where we get to test your knowledge of idiosyncrasies of C. What happens if len up there is -1? Do you know? Yeah. Yeah, so like 2's complement representation of numbers says that the way negative numbers are represented, they're in 2's complement. So -1 turns out to be the bit pattern, FFFFFF, like all ones in binary. And then C says, well, it was declared an int, you treat it as an unsigned int. It's all good. It's just a bunch of bytes. We'll just pass those same bytes in. So now that FFFFF is being interpreted by memcopy not as a signed int, but it's being interpreted as an unsigned int. So now it sees FFFFF and it says, oh, you must mean a really big positive number. And so it'll go copy a really big positive number, like 2 to the 32 minus 1 bytes of data. So it's just endlessly copy way past the end of this thing. So if the attacker controls the value of that len and sets it to -1, or indeed any negative number, then the memcopy will try to write lots of data. Now, what about that bounds check there? Well, if len is -1, then it's not bigger than 64, so the bounds check thinks everything's okay. because -1 looks smaller than the size of the space. So it's being interpreted as a -1 for the bounds check, as a signed int for the bounds check, but it's being interpreted as an unsigned int, a really big number for the copy operation. Okay, so this is called a signed unsigned bug, and it can get you in big trouble. I saw a hand. Okay, yep. Can the attacker lie about what the length is? Well, if the attacker puts in a random positive integer for length, then they won't get anywhere. But you're right. If the attacker puts in a random negative integer for length, then they're copying past the end. Did I answer your question, or did I not get the point?
What if length is 53? The length and the data don't have to correspond to each other.
You're saying, what if the length and the data don't correspond to each other? Yeah, that could be another problem. For this purposes of this question, just imagine that they do somehow correspond to each other. But yeah, okay, for sure. If the attacker could choose len to be 63, but then the data region actually only had 3 bytes allocated for it, then this would actually be reading past the end. So that would be a different kind of problem. You're right. It's just not the problem that I wanted to illustrate with this code snippet. But good. Yes, thank you. You're keeping me honest. Okay, so this code is vulnerable. This code is vulnerable to a buffer overflow, and it's a signed, unsigned int problem contributes to that. So how do we make that safe? The way we make this code safe is declare the length to be a size _t, an unsigned int. So then it'll be interpreted for the bounds check. If you pass in all FFFF, it'll be interpreted as an unsigned int, and the bounds check will say, sorry, that's too much data. Okay, so a good tip when you're writing C code, if you want to be safe, is use safe library functions that won't copy more than you ask for, but also to avoid unsigned problems, whenever you represent a length, and you're going to have to carry these lengths all around so that you can do the bounds checks, store them in a size _t, not an int. I hope you're getting a sense that defending yourself against this in C code can be kind of esoteric, and have a little bit of sympathy for programmers who end up having buffer overruns in your code, because it's very easy to end up with this bug without quite realizing it. Yeah. Okay. All right, so this lecture is getting more technical. So if you were bored the last few lectures, now you get to turn on your coding skills. So now I want you to look at this code for me, and I want you to tell me whether this code is memory safe. So same assumptions as before. The attacker controls the input. They control the data, and they control the length. You can assume that those two correspond. So the attacker's provided a string, and the attacker's chosen the length of it. And I want you to figure out whether this code could have a buffer overrun problem. And I should tell you about malloc, if you don't know what malloc is. Malloc allocates a number of bytes that are passed to it. So you pass to it the number of bytes you want to allocate, and it'll allocate a buffer of that length.